Hi, it's time for another math easy solution. We're going to discuss indefinite integrals, basically go through these and show why it's useful to have this kind of form, and basically, and also not to be mistaken with definite integrals, which I showed in my earlier videos. And basically, I'll just recap. Definite integrals basically are part of the fundamental theorem of calculus. So part one, it says if the function f is continuous on closed interval a and b, closed recall it just means the value at a and b, the f value has a value, so it's defined. You can learn more about that in the video links below. But anyways, so now basically, if you have g of x equals to the integral of a to x of f of t dt, or basically area under the graph, then the derivative of it is equal to derivative of g of x equal to the function f of x inside here. And then that's part one. And part two of the theorem, which I showed earlier also, states basically integral from a to b of fx dx is just equal to the antiderivative at b minus antiderivative at a, where antiderivative is basically the derivative of this capital F of x function is equal to this one here. So this one is antiderivative, or antiderivative of f. That's what this the capital F is. Now this theorem is for definite integrals, meaning that it has a value here or a number, and it's basically the area under the curve there. So now where indefinite integrals come into play is basically when we want to basically find a convenient notation for antiderivative. You can see my earlier video on antiderivatives. Basically, the derivative of it is equal to the function here, so this is antiderivative of f. But basically, we want a convenient notation for it, and that's where the indefinite integral comes into play. And thus, this is what we get the notation for indefinite integrals. Basically, a way of writing the antiderivative. So the antiderivative is equal to just the integral of fx dx, but now we have excluded the a to b or a to x in this, so that it's just a function or a family of functions, and this just means that the derivative of this is equal to this function here, because now we're using the integrals as an antiderivative, because remember, the integrals and derivatives are inverse processes of each other. You can see in the introduction to indefinite integral, to the fundamental theorem, you can see an introduction to that. So if we look at an example here, the integral of basically just say x squared dx here, this is just equal to, if you just think about antiderivatives, this is going to be x to the 3 over 3 plus a constant here, because the derivative of this is going to be, well, x squared here. And then, that's because, the derivative of this is just going to be equal to, well, x squared. The 3 goes down using power rule, 3's cancel, and then the derivative of a constant is 0. But this constant could be any value here, so that you're going to have, in this case, so this indefinite integrals as a family of functions. Family of functions, as opposed to the value here. The definite, that's why you get the definite, just exact value. It's just a value equals area or a number here. So you get a number from this. This one, you get a function here. So there's just a random function. That's, in this case, is this. And then that, just because the derivative is equal to this one here. So now a note that I want to make on basically the fundamental theorem, we'll call it FTC of Calculus. The effectiveness of the fundamental theorem of calculus depends on our supply of antiderivative. So basically, how effective this whole method is of finding area under a curve depends on our antiderivatives, and that's why here's a table of it I got from my calculus book. Basically has a list of many common integrals here, and so this are antiderivatives of here. So it depends on what we know. Some functions we can't get the antiderivative, but the ones we know will help out in our calculations, etc. And all these can be verified just by taking the derivative of the integral here. So this one, for example, the derivative of tan x, t over dx, tan x here, this one is just secant x squared. And you can see a video link below on the proof for that one here. And then, so all you do is you just take the derivative on the ones on the right, and then they should equal to the integral here. That's how you could verify these. And also here's some properties here. If you have a constant integral, you can just take it out. You can see the video link on antiderivatives, which I explain these properties here, etc. here. And this one as well. If the summation of functions, you can just separate them into separate integrals here. And I also want to make an important note on indefinite integrals. Basically, this table of it, etc., well, we adopt this, what the calculus book says, we adopt a convention that when a formula for a general indefinite integral is given, like such as above, it is valid only on an interval depending on the specific integral here. So what this means here is, if you were to look at this, basically this general indefinite integral of this one here, 1 over x squared dx, equals to, well, the antiderivative is just 1 over x negative plus a constant here. So now this is true even though that we know that this is not defined when x equals 0. I'll just write that down here. So this is true even though that this function is not defined at x equals to 0. So then the actual antiderivative is going to be equal to, yeah, so it should equal to something like this here. So negative 1 over x plus c1. This is if basically x is less than 0, and then this is also basically for f if x is greater than 0, because it wasn't defined at x equals to 0 here. And also in here you can't put a 0 inside. You're going to be dividing by a 0 which is not defined, so you have something like this here, and the interval is going to be, you have basically, this is the interval. The interval is, well, it's two intervals in this case, basically from negative infinity. This is open bracket, this is just regular bracket here, or called open, so negative infinity to 0, meaning that it doesn't have to be defined at the endpoints. You can see the video links below on open and closed intervals, and then also from 0 to what was it, plus infinity. So 0 to plus infinity, which this bracket means it doesn't have to be defined at 0. So that's what I want to get to, is just an important note is basically, even though that this just gives us a general antiderivative here, we just still hold this convention, even though that when you actually go in to find the exact one, you have to break it up into the intervals depending on your function. Like this one here is not defined at 0, and it's not defined at 0, so we have to take this into consideration. Well, that's all for today. Hopefully you learn. Next time I'll do some examples on this. And yeah, remember you can always download these notes in the Dropbox link below. And yeah, that's all for today. Hopefully you learned. And yeah, stay tuned for another math easy solution.